American Motors Sales Corporation presents an in-dealership service training program on basic electrical circuitry understanding and diagnosis, circuits used in AMC cars and Jeep vehicles, and how to diagnose malfunctions within the vehicle's electrical systems. The training program includes this film strip and a reference manual. The manual provides detailed job aids to give you a systematic approach to diagnosing electrical problems, as well as a glossary of electrical terms. The film strip presents basic electrical circuit theory and definitions you will need in order to use the reference manual efficiently. The film presents electrical circuit theory and definitions first, and then relates that information to practical applications in your everyday service work. Let's begin by defining an operating electrical circuit as a combination of elements physically connected to provide an unbroken flow of electrical energy from a power source to a device. This device converts that electrical energy to useful work and then returns the unused energy to the power source. In a moment, we'll explain how those parts of the circuit work together. But first, we need some basic definitions so that we're all talking the same language throughout the film strip. In discussing circuits, there are three terms you'll hear repeatedly: voltage, current, and resistance. To explain what each of these is, we'll compare them to a water system, since electricity behaves very much like a liquid. We'll begin with voltage. Voltage is the pressure of electrical energy in a circuit. If we have a tower filled with water, it's obvious that the higher the water level in the tower, the greater the water pressure at the bottom. We measure water pressure in pounds per square inch. We measure electrical pressure in volts. While our water in the tower has pressure, it can do no work until we let it flow out. If we open the pipe at the bottom so that water can flow, we have a current, just like the current in a river. The flow of electrical energy is also called a current, and we measure the amount in amperes, usually shortened to amps. Finally, we have resistance. In our water system, resistance could be the blades of this water turbine. The harder the blades are to turn, obviously, the more resistance they offer. In an electrical system, there is also resistance to the flow of current in the circuit. The first type of resistance we'll be talking about is a working device in a car or Jeep. These working devices, which offer resistance to current flow, are the means of converting electrical energy into useful work. That work can be in the form of heat, light, or motion. The electric rear window defogger is a working device, as is a tail lamp bulb and the blower motor in the heater. All convert electrical energy into useful work, and all present some resistance within the circuit. These working devices are also called loads. Now let's get back to our basic circuit and learn some more definitions. You'll recall that we said every circuit must have a power source, a path for electrical energy to get from the power source to a working device, and a path for that unused energy to return to the power source. In an automobile, that power source will be the battery or the alternator. For the diagnostic procedures we'll be discussing in this program, we can consider the battery the only power source, since all tests are made with the engine not running. Next, the path for electrical energy to flow from the battery to the working device and back again is called a conductor. A conductor is anything that will transmit electrical energy. It may be a wire, a metal strap, or even the metal in the frame, body, and engine of the car. In AMC cars and Jeep vehicles, as in most automotive applications, the path from battery to the working device is a wire, while the path from the working device back to the battery is the car metal itself. This pathway back to the power source is called a ground. We call this a single wire system and say that the working devices are grounded to the metal in the car. Since the working devices use the same ground, the system is also called a common ground system. In some cases, the working devices are surrounded by non-conductors, such as the plastic panel in which the side marker lamp assembly is mounted. In that case, a short, separate ground wire must be run from the working device to some point on the metal of the car. Next, let's review what we've learned so far. There's no need to write down any answers, since this review is for your information only, to give you an indication of your progress. Mentally answer the questions in the next few frames. The three essential elements of every circuit are a power source or battery would also be correct, a conductor to act as the path for current to flow, and a working device or resistance that converts electrical energy into heat, light, or motion. Now, match the lettered word that most accurately describes each of the numbered words. Voltage is electrical pressure. Amperage is the amount of electrical current flow. And resistance, in this case, is the working device in an automotive circuit. Now, let's get back to our basic circuit and add some accessories. These are things that control or protect the circuit, such as switches and fuses. A switch opens or completes a circuit. When it opens the circuit, it interrupts the flow of current. It provides a handy way to turn the working device on or off. It works because of what we have already learned. In order to operate, a circuit must have a continuous path for the current to flow from the battery to the working device and back to the battery. A fuse is a component used to protect the circuit from an overload. Later, we'll discuss what an overload is and what can cause it. But for now, you need know only that an overload causes a circuit to heat and will eventually let the conductor burn in two. A fuse is a deliberate weak link conductor in the circuit that will burn out long before the rest of the conductor burns. AMC cars and Jeep vehicles use three kinds of fuses, but all are designed to do the same job: break the circuit before an overload can damage it. All of you are familiar with the cartridge fuse. It is a replaceable weak link in the circuit. Another kind of fuse, the fusible link, is simply a length of wire, usually smaller in diameter than the rest of the circuit conductor, that will burn out in the event of an overload. The third type is a circuit breaker, which is a specialized type of fuse. It opens the circuit temporarily in the event of an overload. The heat generated by the overload causes it to open, and it closes again when it cools off. The other common circuit accessory is a variable resistor, such as the rheostat used to dim the dash lights. Remember that a resistance tries to hold back the flow of electricity. The variable resistor does just that, allowing more or less current to flow to the dash lamps, making them bright or dim to suit the driver. Up until now, we've used examples of simple circuits with a single working device or load. We've learned what it must have to operate and what some of the circuit accessories are. But in AMC and Jeep vehicles, there are no simple circuits because it is more efficient to combine several such simple circuits into one of three types of more complex circuits. These three types of circuits are called series, parallel, and series parallel. Let's begin with the series circuit. In a series circuit, the loads, in this example the bulbs, are connected so that there is only one possible pathway from the battery. The current must flow through one device to the next. Since a circuit must have an unbroken path from power source to working device and back to the power source, you can see what happens in a series circuit if the current flow is broken at any device. If a series circuit is interrupted at any point, then all working devices on that circuit will cease to operate. For example, if one of the bulbs were to break, all the bulbs hooked up to this series circuit go out. The important point to remember about series circuits is that they allow current to flow only in one pathway through all the devices in the circuit. This property of series circuits limits their use. We would not want all lights to go out if only one bulb were burned out or broken. But that same property is also useful, as we'll see in this example. The coolant temperature warning lamp is connected in a series circuit. Notice that voltage is available up to the temperature sending unit constantly. But the circuit cannot be completed and the lamp will not light until the circuit is completed through a temperature-sensitive sender located in the engine block. This sender unit will not complete the circuit unless the engine reaches a critical temperature. The next type of circuit you'll find in your routine work is a parallel circuit. Parallel circuits have their loads connected in such a way that current can flow through all of the loads and back to the battery. Each working device can be shut off without affecting the others. Notice in this drawing that the working devices are connected in parallel rows in such a way that current can flow both through and around any individual device. But remember, in an automotive single-wire system, the conductor carrying current back to the battery is the car metal itself. A parallel circuit in a Jeep, for example, would actually look like this. Notice that each load is individually grounded so that current can flow through it directly back to the battery. The final type of circuit you will see is actually a combination of the two you have already studied. It's called a series parallel circuit. It contains the elements of both series and parallel circuits. In this example, the headlamps are connected in parallel, and that means if one bulb burns out or a wire to it is broken, the other will still operate. But when we want to turn the lights off, we want to turn them both off. A switch connected in series with the main feed wire to the headlamps does the job. Since it is connected in series with the circuit, opening the switch cuts off all current flow to the entire circuit, and what we have now is a series parallel circuit. Now let's review the types of circuit we've discussed. What type of circuit is this? Parallel, series, or series parallel? It is a parallel circuit. You can identify it quickly by noticing that each working device is individually grounded. Now look at this closed series parallel circuit. What happens if we open switch A and leave switch B closed? Since switch A is connected in series, it breaks the flow of current and all of the lights on the circuit would turn off. Now, what happens if we open switch B with switch A closed? Since switch B is connected in parallel, it would turn off this light and all others would continue to burn. Now that we understand the types of circuits used in AMC cars and Jeep vehicles, let's see how that knowledge can be applied to everyday service problems. The test instruments you'll use most often for simplicity in troubleshooting will be a 12-volt test lamp and a jumper wire. If you are unfamiliar with these basic test instruments, read about them, their use, and how you can make your own in your reference manual. These two basic tools will handle most troubleshooting chores. Special problems, such as those requiring electrical test equipment to diagnose, will be covered in another training program. The wiring diagram is one of your most valuable tools for troubleshooting a car's electrical system. Your technical service manuals contain wiring diagrams or schematics like this for all AMC cars and Jeep vehicles. These diagrams use drawings of the various working devices rather than more technical electrical symbols to help you locate a particular circuit quickly by visual association. The wiring diagram lets you trace a circuit on paper. You can see where a particular wire goes and how it should be connected without having to remove an instrument panel or cut open a wiring harness. When using the wiring diagram, notice that each wire is identified with a color code. This one, for instance, means that the wire is colored dark green with a white stripe called a tracer. Now, all you have to do is find the dark green wire with the white tracer at the back of the starter solenoid in the car, and you know where it goes and what it does just by looking at the wiring diagram. The wiring diagram will help you find a problem faster and easier through the use of a procedure called common point testing. Common point testing saves you the trouble of having to trace each circuit all the way from the battery through the load and back to ground. It is a simple, sensible shortcut. Here's how it works. Let's say one of the rear side marker lamps doesn't light. You could begin by tracing the wiring all the way back from the headlamp switch, but that's not necessary. The first and easiest thing to do, of course, is check the side marker bulb and socket. Is the bulb burned out? Is the socket corroded? If neither of these conditions seem to be causing the problem, what next? If you look at the schematic, you'll notice that both side marker lamps and the tail lamps are fed from splice W. Since the other lamps in the circuit light, you know that the problem with the side marker, which is out, must be between the common point at splice W and ground. In this particular circuit, we can isolate the problem even further by connecting a test lamp between a known good ground and the contact in the socket which connects to splice W. If the test lamp lights with the headlamp switch on, the problem has to be in the ground side of the circuit. Since there's a common ground at splice V and the other bulbs light, you know the problem must be between the socket and splice V. Of course, if the test lamp does not light when you connect it between the side marker and ground, it tells you that there is a problem between the socket and splice W of the positive conductor. Here's another example. Let's say both backup lamps don't work. Since neither of them work, it's a good bet that the problem is more serious than a burned-out bulb or fuse. Since you know the backup lamps are controlled by a switch, you could start at the backup switch, but that's the hard way. Checking your diagram would show you that the backup lamps use a brown wire for a source of voltage. It also shows that the brown wire runs to a body harness connector. All you need to do is put the car in reverse, turn on the ignition, go to the body harness connector, and test the brown wire connection with a test lamp. The test lamp should light. If it does, you know the circuit from the battery to the body harness connector is good. The problem has to be on the backup lamp side of the connector. Start there and trace down your problem. If the test lamp doesn't light, it tells you the problem is between the connector and the power source. Go back to your wiring diagram and you'll find that the brown wire surfaces again at the DT terminal of the dash connector. The wiring code on the connector can be read from inside the car. Use your test light there, and you can isolate the problem to the backup lamp switch or to the wiring harness between the dash and the body harness connector. Remember that common point testing is a smart shortcut that saves you time and trouble. Using it requires reading the wiring diagram and understanding the color coding of wires. Another troubleshooting shortcut is something called forward diagnosis. Forward diagnosis is the combination of applied knowledge and common sense. In other words, think through the problem before trying to solve it. Let's go to our backup lamp problem again, but this time, let's say only one backup lamp doesn't work. It's time for some forward diagnosis. We could use common point testing to track down the problem, but even better, take a moment to think through the problem. It's pretty obvious that the backup switch is working. Otherwise, neither backup lamp would work. You can be pretty sure then that the problem is either a burned-out bulb, a bad ground, or a fault somewhere in here between the bulb and splice V shown on the wiring diagram. Always take the time to think through the problem before beginning hands-on troubleshooting. By now, you should have a basic understanding of enough circuit theory and practical application to troubleshoot most basic electrical problems using your wiring diagrams. The next step in your training program is to apply this understanding to specific situations. Your reference manual discusses 6, and there are only 6 possible malfunctions with any automotive electrical circuit. Get to know these 6 specific problems thoroughly, how to recognize and confirm them, what to do about them. Begin reading your reference manual right away while the information in this film is still fresh in your mind. Together, this film and the reference manual will help make you a more efficient and more professional AMC and Jeep service mechanic.